Imagine you are drifting weightlessly in the silence of space. There is no up or down, only a void stretched infinitely in all directions, peppered with distant lights. Around you, silence presses in, the kind of silence that feels eternal. The cold is not just a temperature, it is an absolute, penetrating stillness that seeps into every atom of your being. And before you, from the emptiness, something begins to emerge. A world that defies understanding, a planet with oceans of molten diamonds and iron rains falling through dense, exotic atmospheres. These are not the settings of dreams or science fiction. They are real, and they are out there. The universe, in all its unimaginable scope, is home to worlds more alien than we could have dared to imagine. Planets where a single day outlasts a year. Planets where the skies are black, not from the absence of light, but because their atmospheres are so crushingly dense that no sunlight ever reaches the surface. Giant planets with endless storms that have raged since long before human history began. Places that echo Earth just enough to stir longing and fear. Why are these strange, distant worlds so important to us? Why do we feel drawn to them, as if searching for a cosmic mirror in which we might see our own reflection? Perhaps it's because in understanding them, we inch closer to answering the most profound question we can ask. Are we alone? If you've ever found peace in the quiet of the stars or sought comfort in the idea that the universe is vaster than our troubles, then you belong here. Join us as we journey through the cosmos. Subscribe, support, and become part of our celestial family. Your presence helps us keep the flame of curiosity burning through the long nights, bringing knowledge and peace to every restless soul beneath the stars. Look up at the night sky. Each twinkling star might be a sun. Each sun might have its own family of planets. Each planet a story yet untold. The creation of those worlds begins in the deep, cold emptiness between the stars. There, colossal clouds of interstellar dust and gas drift quietly until something changes. Gravity stirs, a whisper becomes a roar. The cloud collapses inward, heating up, compressing, igniting. A star is born. Around this newborn sun, leftover gas and dust begin to spin in a flat, swirling disk. Over millions of years, this protoplanetary disk becomes the cradle of planets. Microscopic grains of dust collide and stick. Pebbles form, then boulders, then mountain-sized chunks, planetesimals. These ancient building blocks collide, fuse, and grow, each collision a violent act of creation. Slowly, worlds emerge. Near the star, only metal and rock can survive the blistering heat, forming small, dense planets like Mercury, Venus, Earth, and Mars. Farther out, where it's cold enough, ices and gases join the mix, giving rise to giant worlds like Jupiter and Saturn, and icy giants like Uranus and Neptune. This architectural layout, rocky inner worlds, gaseous outer giants, is just one blueprint. The cosmos holds infinite variations. Some planetary systems are chaotic tangles of giants huddled close to their stars. Others have planets dancing between two suns, caught in elegant gravitational ballets. Some systems expel planets into the void, creating rogue worlds wandering alone through the darkness. With every telescope, every mission, we reveal more, planets of such strangeness they rewrite what we thought we knew. Scorching gas giants hugging their stars, rocky worlds that spin backwards, and moons that may harbor oceans hidden beneath ice. Our own solar system is just a whisper in a chorus of voices. Now, imagine those primordial clouds again, those slow, patient architects of stars and planets. Somewhere right now, in the shadows of a distant galaxy, dust is becoming stone, stone is becoming world. Maybe it will be barren, maybe it will bloom, Maybe one day beings will look up from its surface, their eyes filled with wonder, and ask the same question we ask under our stars. Are we alone? Beyond the pale light of Mercury and the violent pressure of Venus, we arrive at a place unlike any other. Our home, Earth, suspended in darkness, glows with a serene blue brilliance. It is a fragile sphere of life wrapped in a thin veil of atmosphere, rotating quietly in the warmth of a yellow star. From space, it seems peaceful, but hidden within its clouds, oceans, and lands is a complexity that has taken billions of years to sculpt. Here, water flows freely across continents, surges in tides, evaporates into vapor, and rains back onto soil and rock. Earth is an orchestrated balance of forces: geological, chemical, biological. Its atmosphere just thick enough to shield life from cosmic radiation, yet thin enough to let sunlight in, is composed with a precision that makes life possible. With 21% oxygen, 78% nitrogen, and traces of carbon dioxide, it is both a protective skin and a living system. The planet's magnetic field, born from the dynamo motion in its liquid iron core, acts as a guardian, deflecting solar wind and cosmic rays. Without this invisible shield, Earth's surface would be stripped bare like the moon. But it is not just protection that the magnetic field offers. It also reveals itself through beauty-dancing auroras of green and violet over polar skies, silent, ethereal, and electric. Our moon, a companion formed in a cataclysmic collision, helps stabilize Earth's rotation. Its gravitational pull orchestrates the tides, stirring the oceans in cycles that may have played a crucial role in the emergence of life. No other planet in our solar system has a satellite so large in proportion to its host, a cosmic coincidence, or a stroke of design from the hand of chance. And then there is Earth's geological life. Tectonic plates slide over molten currents, shaping continents, birthing mountains, and pulling ocean floors beneath land in an endless recycling of the crust. Volcanic eruptions and earthquakes are not anomalies, but symptoms of Earth's living geology. This motion helps regulate the carbon cycle, a planetary breath that stabilizes the climate over millennia. But perhaps most striking of all is the fact that Earth is covered by oceans. More than 70% of the surface is water. And in this water, in tide pools, thermal vents, and shallow seas, life began. Single cells evolved into colonies, then organisms, and eventually creatures that breathe, walk, think, and wonder. Evolution, powered by sunlight and time, gave rise to consciousness and eventually to us. From Earth's surface, our gaze turns outward again, to Mars, the red planet. Its surface, seen through telescopic eyes, hints at a turbulent past. Great canyons slash the planet's crust. Extinct volcanoes reach skyward. Dry riverbeds trace the ghosts of ancient water. Once, perhaps, Mars was not so different from Earth. Mars is a cold, arid place now. Its atmosphere is thin, only 1% of the pressure of Earth's, and composed mostly of carbon dioxide. Yet there is water, frozen in the poles, perhaps hidden in underground aquifers. And there is time. A Martian day is just 40 minutes longer than ours, and its seasons, though harsher, follow a familiar rhythm. Billions of years ago, Mars had a thicker atmosphere and liquid water on its surface. Rovers have traced the pathways of rivers, the shores of lakes. Sedimentary layers tell stories written by flowing water and wind. What happened? Mars lacks a magnetic field to shield it. The solar wind stripped away its atmosphere, and with it, its warmth and water. Yet it is not a dead world, far from it. Beneath its surface, some scientists believe microbial life may still hide, safe from ultraviolet rays and cosmic radiation. The search for that life is one of humanity's great scientific quests. If we find life on Mars, even the simplest form, it will mean that life is not a miracle confined to Earth. It will mean the universe teems with potential. But Mars is not just a scientific target, it is a destination. Elon Musk dreams of colonizing it. NASA plans human missions. The challenges are immense radiation, low gravity, psychological isolation. But the goal is clear: to become a multi-planetary species. If we can survive and thrive on Mars, it will mark the first great leap into a future among the stars. And still, as we venture outward, we look back. Earth is warm and blue, Mars is cold and red. Two neighboring planets, once perhaps alike, now separated by a cosmic fork in the road. One cradles life, the other bears its fossilized shadows. The contrast is a reminder of how delicate the thread of habitability truly is. Approaching Jupiter is like nearing a living storm the size of eternity. Its stripes are not just color, they are atmospheric rivers moving at hundreds of kilometers per hour. Each band a distinct climate zone locked in battle with its neighbors. And there, nestled among the roiling chaos, is the Great Red Spot, a cyclone so vast that 3 Earths could vanish inside it. It has raged for centuries, an ancient scar in the fabric of the sky. Jupiter is not merely a planet, it is a system unto itself. With more than 90 known moons, it is a miniature solar system within our own. Some of these moons are among the most fascinating bodies in the cosmos. Ganymede, the largest moon in the solar system, is even bigger than Mercury and has its own magnetic field. Europa, smooth and pale, hides a subsurface ocean beneath its icy crust, an ocean that may harbor life. Volcanic Io, constantly reshaped by the tidal forces of Jupiter's gravity, is the most geologically active place we know. The sheer gravitational dominance of Jupiter helped shape the entire solar system. It may have flung countless comets and asteroids toward the inner planets, delivering water to Earth or perhaps posing deadly threats to early life. Its presence is both protector and destroyer, guardian and tyrant. And then there's Saturn, further out but no less majestic. If Jupiter is power, Saturn is grace. Its rings, seen from afar, are impossibly thin, made of ice and rock and dust, suspended in a silent ballet. Each particle in those rings follows its own orbit, yet together they create something luminous and ethereal. They are the most delicate structures on a planetary scale, a cosmic lacework 100,000 kilometers across, but only a few dozen meters thick. Saturn, too, has moons worth marveling over. Titan, with its thick, nitrogen-rich atmosphere, has lakes of methane and ethane. It rains there, but not water. A methane cycle mirrors Earth's hydrological one, making Titan a frozen analog of our planet. Beneath its crust, like Europa, may lie a hidden ocean. And then there's Enceladus, a tiny moon that shoots plumes of water vapor into space, suggesting a subsurface sea kept warm by tidal forces. We have flown through those plumes. We have tasted the ocean of another world. The outer planets, Uranus and Neptune, are stranger still. Tilted on its side, Uranus rolls through space like a barrel, its seasons extreme and long. Its atmosphere, a mix of hydrogen, helium, and methane, gives it a ghostly cyan hue. Neptune, deep blue and distant, hosts the fastest winds in the solar system, up to 2,000 kilometers per hour. It is a frozen fury at the edge of sunlight's reach. These planets and moons are not only physical worlds, they are emotional metaphors. Jupiter is the patriarch, Saturn the archivist, Uranus the exile, Neptune the dreamer. They remind us that every place, no matter how distant, carries a story, and that our own story is richer for knowing theirs. Beyond Neptune lies the Kuiper Belt, home to Pluto and countless icy bodies. Once a planet, now a dwarf. Pluto revealed its heart to us literally when New Horizons flew past and captured that now iconic image, a frozen plain in the shape of a heart, made of nitrogen ice. It is a world of mountains, glaciers, and complex geology. Not dead, not simple, just far. The solar system does not end there. The Oort cloud, a spherical shell of icy debris, marks the boundary of the sun's gravitational dominion. Some of its objects take millions of years to orbit once. It is from here that long-period comets arrive, intruding into the inner solar system like messengers from the dark. These places, Jupiter, Saturn, Uranus, Neptune, Pluto, remind us of scale, of time, of complexity beyond imagination. They challenge our notion of habitability, of what is alive, of what can be known. Each world is a possibility, each moon a mystery, and somewhere among them, perhaps in a warm ocean beneath ice, or in a cave shielded from radiation, there is life. Simple, silent, surviving, or maybe not. Maybe we are alone. But whether life is out there or not, these distant orbs change us. To see them, to name them, to visit them, is to understand ourselves better. We are not confined to one world. We are not prisoners of gravity. We are explorers, dreamers, makers of meaning from rock and gas and light. And now we turn our eyes outward again, past the sun's final breath, past the frontier of our solar system, toward the stars. Between our solar system and the next, there is no road, no air, no landmarks, only distance measured not in kilometers or miles, but in time and silence. This is the interstellar medium, a vast, thin haze of gas and dust and fields that stretches for light years in every direction. It is neither empty nor welcoming. It is the space between homes. To travel here is to confront isolation on a scale unimaginable. Voyager 1, launched in 1977, now coasts through this void. It carries with it a golden record images, sounds, greetings, our planetary message in a bottle, but no one has yet replied, and maybe no one ever will. Beyond the heliopause, where the solar wind yields to interstellar pressure, the physics changes. Particles move differently. Fields behave oddly. This region, once purely theoretical, is now partially mapped thanks to probes like Voyager. Still, we have only dipped a toe into the cosmic ocean. The stars we see twinkling overhead are still impossibly far. The nearest is Proxima Centauri, just over 4 light-years away. At the speed of the fastest spacecraft we've built, it would take over 70,000 years to get there, yet we dream of reaching it. Proxima b, a potentially habitable planet in that system, has ignited hopes of another Earth. But even the most optimistic missions like Breakthrough Starshot, which proposes sending gram-scale probes at 20% the speed of light, remain decades from realization. Still, the physics of such travel stirs imagination. Concepts like light sails, fusion propulsion, antimatter drives, and even warp bubbles stretch the boundary between science and speculation. Some of these may prove viable, others may remain beautiful ideas, but each is a step toward breaking the tyranny of distance. Beyond technology, interstellar travel demands a transformation of thought. To cross between stars is to leave behind everything familiar, not only home and light and time, but even language. The vastness is humbling. It reshapes questions of survival, society, and self. Could we remain human scattered across such gulfs? Would a generation ship preserve culture or birth something new entirely? The philosophical weight is enormous. To voyage outward is not only a technical act, it is a moral one. It forces us to ask why we go, what we carry, what we leave behind. It turns space into a mirror. And then there is the quiet, the cosmic background hum. The echo of the Big Bang permeates all. It is not sound in the usual sense. There is no air to carry vibration, but a whisper of radiation, uniform, omnipresent, a fossil from when the universe was just 380,000 years old. To measure it is to look backward in time, to a moment when atoms were first able to form and light was finally free to travel. The background radiation is smooth, but not perfectly so. Tiny fluctuations, mapped in exquisite detail by satellites, tell us about the early universe's density, temperature, and shape. These are the fingerprints of inflation, an era when the universe expanded faster than the speed of light. This expansion smoothed the cosmos, made it flat, and planted the seeds of all structure. Inflation, still theoretical but well supported by data, changed everything. It answers puzzles that once confounded cosmologists: why the universe is so homogeneous, why its geometry is flat, why there are no magnetic monopoles, but it raises new questions too. What drove inflation? What ended it? And could it still be happening elsewhere? Some theorists propose eternal inflation. In this view, our universe is just one bubble in an infinite foam, each bubble a separate cosmos with its own laws and constants. This multiverse, as strange as it sounds, may be a consequence of high-energy physics. It could explain why our universe is so finely tuned for life, not because it was meant to be, but because we happen to be in a bubble where life is possible. These are not idle speculations. They emerge from equations, from observations, from the clash of quantum mechanics and general relativity, yet they point beyond science. They edge toward meaning. To imagine other universes is to expand our definition of reality, to accept that what we see, the stars, the galaxies, the void, is only a fraction of all that exists. And perhaps, just perhaps, that there are other versions of ourselves, living other lives in places that will forever remain beyond reach. Still, our focus returns, not to what might be, but to what is. The interstellar medium, the cosmic microwave background, the physics of voids and fields, these are not merely abstract. They are the canvas on which our story is painted. And through this canvas, something else moves. A ripple, a wave, not of light, but of gravity itself. Shall we listen to it? The dance of existence continues in silence beyond the cosmic horizon. All that has come before black holes, dark matter, exoplanets finds a home in a universe that is still expanding, still evolving. But beyond the phenomena we observe, the deepest questions begin. What gave rise to this universe, and why these laws, these constants, this balance that allows complexity, life, and awareness? In the first trillionths of a second after the Big Bang, something extraordinary happened. Not the explosion itself that's a metaphor, but the rapid swelling of space itself. Inflation, a period when the universe ballooned faster than light, driven by a mysterious energy embedded in the quantum vacuum. During this brief era, quantum fluctuations, microscopic wrinkles in the energy field, were stretched to cosmic scales. They became the seeds of all future galaxies, all future us. These primordial ripples are imprinted in the oldest light. We can detect the cosmic microwave background. It shows us tiny variations in temperature, barely 1 part in 100,000. But those tiny differences determine the shape of the universe to come. Regions slightly denser than average drew more matter, forming stars, clusters, and vast cosmic filaments. The great web of the universe began as a trembling in a quantum field, and this is where theory brushes against the edge of the unknowable. Inflation may not have been a one-time event. Some physicists propose eternal inflation, a bubbling cosmos where each bubble is a universe, our universe, then is one among an infinite multiverse. Each bubble may have different physical laws, different particles, even different dimensions. Perhaps, in one, stars never formed. In another, time runs backward. In another, life is silicon, not carbon. These ideas are not just speculative dreams. They emerge from the math that governs the quantum and cosmological realms. String theory, for instance, suggests a universe with 10 or more dimensions, most curled up tightly, beyond our detection. It offers a framework where gravity and quantum mechanics can finally merge. But even if these theories are right, how could we ever test them? What would it mean to peer beyond our cosmic bubble? Could gravitational waves from other universes leave a scar in our sky? Could high-energy particles from a neighboring cosmos punch through the veil? Scientists seek signatures in the sky, unusual cold spots, unexpected alignments, anomalies in the cosmic background that might hint at collisions with other universes. And still, the question deepens: why is there something rather than nothing? Why these laws, this geometry, this dance of energy and entropy? The anthropic principle suggests we live in a universe compatible with our existence. Others might be barren, short-lived, or chaotic. But this is not a satisfying answer. It begs for more. It hungers for insight. Philosophers and physicists converge here. Some suggest the universe is a mathematical structure, existing because mathematics is inevitable. Others imagine a self-creating cosmos, one that brings itself into being through a loop of quantum cause and effect. Still others invoke the simulation hypothesis that all of this, from quarks to quasars, is information processed in some vast computational substrate. No matter the answer, the search itself is sacred. And so we push forward. We build better telescopes. We refine our theories. We teach our machines to sift patterns from noise. We test the edge of what is knowable. Yet in the midst of this cosmic ambition, we return to something deeply human: the awe of seeing a sunrise, the touch of a child's hand, the memory of a loved one. These, too, are part of the universe, no less fundamental, no less cosmic. The neutrinos passing through your body right now were forged in stellar cores and supernovae. The calcium in your bones, the iron in your blood, the oxygen you breathe, all made in ancient stars. You are not just in the universe, you are of it. A way for the matter to become self-aware, to dream. And dream we must, of life beyond Earth, of civilizations rising among exoplanets, of technologies that fold space, of messages carried not by light, but by gravitational whispers. The Voyager probes, launched in the 1970s, now drift through interstellar space, carrying golden records etched with music and greetings from Earth. They are tiny ambassadors, drifting farther from us each year, but also closer to eternity. We will go further with light sails, fusion drives, and maybe someday wormholes. We will seed new worlds, if not with our bodies, then with our minds, our machines, our stories. Perhaps the universe's greatest mystery is not why it exists, but why it allows for beings who can ask why. Beings who can fall in love, grieve, create symphonies, and build particle accelerators.
Light takes 8 minutes to travel from the sun to Earth. That means everything we see in the sky is already in the past. Even the nearest star is not quite what it seems. Not in this moment. It is what it was. That idea is simple. Measurable is also profound. It means that when we look outward, we look backward. Every photon that reaches us is a silent witness from a different time. A cosmic delay is stitched into the very act of seeing. This delay is not trivial. A star 100 light-years away sent its light before the first electronic computers existed. Some galaxies shine from distances so great, their light began the journey long before our solar system formed. These aren't poetic metaphors. They are testaments to the scale of time and space we exist within. We see the present in our hands, but the sky shows us what is gone. A telescope is a time machine pointed up. Distances in kilometers collapse under the weight of this cosmic scale. What is 100 million kilometers to the sun when the nearest galaxy lies millions of light years beyond that? Traditional units become absurdly small. So we surrender them. Instead, We count in time seconds, hours, years of light. 1 light second is 300,000 kilometers. 1 light year is nearly 10 trillion kilometers. Our Earth, rotating and tilting modestly in its orbit, is wrapped in a bubble of delayed information. We do not see space, we see ancient signals. Yet with this simple conversion of distance into time, a remarkable clarity emerges. To say a galaxy is 10 million light years away is to say we are witnessing it 10 million years ago. With every step farther outward, the universe reveals more of its youth. It's like peering through layers of sediment where deeper means older, and older means stranger. This is not just a scientific reality, it is a narrative structure written into the fabric of the universe. The farther you look, the more primal the story becomes. Even the scale of our own solar system, which seems vast, folds quickly under cosmic perspective. Light takes mere hours to cross from end to end, touching Pluto's orbit in about 10 hours. But then, to reach even the next star years, to leap to the stars beyond that centuries of light travel. Our Milky Way contains hundreds of billions of stars, each separated by spaces so wide the nearest neighbors are measured in parsecs, a unit born from trigonometric subtlety. Hold up a finger at arm's length, close one eye, then switch. The finger jumps. That is parallax, the change in perspective from two viewpoints. Astronomers use Earth's orbit as the arm's length, 1 astronomical unit wide. A nearby star seen in June will appear in a slightly different position 6 months later. From this shift, and the angle it creates, they calculate the distance. This method works well for stars a few hundred light years away. Beyond that, the angle becomes too small. The stars sit too still. So astronomers reach for brightness. A nearby star's absolute brightness, known from parallax, becomes a candle to compare with more distant, similar stars. The dimmer a match appears, the farther it must be. But the light weakens with distance not linearly, but by the square twice as far is 4 times as faint. The universe does not give up its depth easily. Every measure is an inference. Every distance is reverse engineered from delay, dimness, and distortion. Beyond our galaxy, more galaxies float, millions of them. They form clusters and superclusters, stretching across the cosmos like veins in stone. Each is a swirling storm of stars, billions strong. These galaxies are not merely far, they are ancient. Their light began before life ever stirred on Earth. The space between galaxies makes even the vastness of the Milky Way seem intimate. Yet, within our own corner, stars show their secrets. Many are not solitary. They are paired, even tripled gravitational families orbiting one another in long, slow dances. Binary systems are common, and they vary wildly. Some stars orbit each other leisurely over decades. Others spin so closely they exchange matter, heat, and energy, shifting form and character over time. The sky is not quiet. It is teeming with motion, with evolution, with competition. The average distance between stars, about 1 parsec, is an enormous gulf. That's 20 million times the diameter of our sun. So despite the dazzling number of stars in the sky, they are scattered thinly across space, each lonely in its sphere, but their variety is endless. Stars differ in color, brightness, mass, and age. Their color reveals their temperature, and their brightness hides a story of size, heat, and internal fury. And imagine a star not as a point of light but as a globe of gas, suspended in nothing, held together by gravity and aglow with nuclear fire. The cooler stars burn red, the hotter ones, blue-white. Their placement in the Hertzsprung-Russell diagram, a map of stellar characteristics, traces a path from dim red dwarfs to blistering blue giants. The sun sits among the yellow-white, a modest beacon with a surface temperature of nearly 6,000 Kelvin. It is neither young nor old, neither large nor small, and yet the sun is the threshold. It is the standard by which others are judged. We speak of solar masses, solar luminosities. In that framework, some stars blaze with the force of 10,000 suns, Others, white dwarfs and red dwarfs, whisper with faint, dying light. Some have surfaces as hot as 25,000 Kelvin. Others linger near the threshold of fusion, barely radiating. A few are mere ghosts dense, dim remnants cooling over eons. The universe permits this diversity. It breeds it, encourages it, then watches as stars live, compete, and die. What we see in the sky is not static. It is history. It is rivalry. It is the consequence of physics unrolling across billions of years. And every glimpse we catch is shaped by the most fundamental truth of all: we are always looking into the past. The light that reaches us carries more than distance and delay. Encoded in every wave and photon is the temperament of the star that created it, its temperature, its rhythm, its weight. Most stars radiate steadily, but some flicker and swell like living hearts. These variable stars pulse in brightness, their outer layers expanding and contracting in cosmic breaths. The rhythm is not random. It is precise, often tied directly to a star's intrinsic brightness. Measure the pulse, and you know the power. Measure the power, and you know the distance. This relationship, first discovered by Henrietta Leavitt in the early 20th century, gave astronomers a tool as elegant as it is powerful. The longer a variable star's pulsation, the more luminous it is. By comparing that true luminosity with how dim it appears from Earth, we can measure its distance. These stars, called Cepheids, are among our most reliable beacons. They populate our galaxy and others, blazing like lighthouses across the sea of space. Some, like Polaris, throb gently. Others vary more wildly, but each is a metronome in the dark, ticking out the depth of the cosmos. These Cepheids are not mere curiosities. They are evolved giants, larger and more massive than the Sun, nearing the end of their stellar lives. Their luminosity is tremendous, often thousands of times that of the Sun. They have passed through earlier stages of fusion, consuming hydrogen and now oscillating as their internal structures search for equilibrium. In these fluctuations, they sing, their surfaces ripple, their cores heave. The starlight flickers, but not in chaos. It flickers with the precision of a clock built in fire. Deeper inside the stars, away from surface rhythms, something more intimate occurs. A balance is constantly being negotiated. Gravity pulls inward, pressure pushes outward. For a star to exist, it must strike a perfect truce between collapse and explosion. The inner heat provides the pressure. That heat comes from nuclear reactions. Without them, the gravity would win. The star would fall in on itself and disappear. In the core of our Sun, the temperature reaches 15 million Kelvin. The pressure is so intense that gas behaves unlike any we experience on Earth. It is plasma fully ionized, with atoms stripped of their electrons. The particles move with furious speed, crashing into one another, generating radiation not in gentle visible light, but in harsh X-rays. That radiation does not stream freely to the surface. It is trapped, scattered, absorbed, and re-emitted endlessly, taking millions of years to escape. The light we see from the Sun today began its journey long before the first humans walked upright. This is not metaphor. It is delay built into the Sun's anatomy. The photons that finally emerge have bounced 1 trillion times through a crowded furnace of plasma. Only when they reach the convective outer layers can energy rise more swiftly, carried upward by boiling gas currents like water in a pot. In smaller stars, convection dominates. In larger ones, radiation carries more of the load. But in every case, the star finds a way to ferry its energy from core to surface and then into space. This energy flow is not silent. Inside the star, pressure waves move sound. In a sense, though not in air, these acoustic waves reflect and refract, creating complex standing patterns. Each star is a resonating chamber, humming with its own voice. In the Sun, these vibrations tell us about the interior we cannot see. Helioseismology, The study of solar sound reveals the shape of its core, the depths of its convective zone, and the hidden churn of its layers. The sun is not still. It rings like a bell. It hisses like steam. And those sounds, though silent to us, drive physical changes across its atmosphere. The outermost layers, known as the corona, are paradoxically hotter than the surface below, 1,000,000 degrees or more, heated by the chaotic flow of sound and magnetism. The thinness of the corona prevents it from radiating its heat away. Instead, it explodes outward, carried by charged particles in what we call the solar wind. This stream of gas flows through the solar system, shaping planetary atmospheres, buffeting magnetic fields, and whispering to every satellite and probe. Other stars possess their own stellar winds, some gentle, others savage. A few are so intense they tear the stars apart over time. Gas flows away in rivers, accelerated by radiation and magnetism. In some stars, the shedding is slow and sorrowful. In others, it is a tempest. The universe does not mandate serenity. Some stars live like monks. Others die in flames. Yet all of them are powered by the same fundamental engine, nuclear fusion. At its heart, a star is a reactor. It fuses hydrogen into helium, converting mass into energy. But this process is not simple. Protons are positively charged. They repel each other. To fuse, they must come unimaginably close. Even in the center of the sun, with temperatures soaring and particles speeding, most collisions do nothing. Only occasionally 1 in a trillion does quantum tunneling allow a proton to sneak past the barrier, to touch, to fuse. This is the first of 2 great hang-ups. The second is subtler. Even when 2 protons meet and bond, they must transform. 1 proton must become a neutron. This requires a weak nuclear interaction, an unlikely quantum event. On average, a proton in the sun's core waits billions of years to undergo this change. But there are so many protons that some are always reacting, keeping the fire alive. Fusion releases energy because the helium nucleus that results is slightly less massive than the 4 protons that formed it. The missing mass becomes energy, flung outward as heat and light. The process is known as the proton-proton chain. In larger stars, a more complex cycle dominates the carbon-nitrogen-oxygen cycle, or CNO. It is less dependent on quantum chance and more efficient at higher temperatures, but all fusion in stars has the same goal: transform mass into energy, and in doing so, resist collapse. The stars are not static. They are not simple. They are delicate balancing acts, held between gravity and radiation, between collapse and expansion. They are ancient engines wrapped in fire, whispering across the cosmos through light and sound. And yet, even they have lifetimes. Their fuel is not infinite. Their patience runs out. And when it does, something else begins. A star's death begins in silence. Its core, having spent millions or billions of years transmuting hydrogen into helium, reaches a point of exhaustion. The fire wanes not everywhere, but in the heart where fusion once blazed cleanly and steadily. What remains is a cinder of helium, hot and inert. The outer layers, still glowing, still shedding light, no longer draw energy from within. The balance tilts. Gravity, ever patient, resumes its slow encroachment. The core contracts. In falling inward, it releases gravitational energy, heating the surrounding layers. A shell of hydrogen outside the core begins to burn, reigniting in a fury that pushes the outer envelope outward. The star swells, its surface cools. It becomes a red giant. The transformation is not immediate, but when it comes, it is dramatic. A star that once shone with a steady yellow-white glow now glows red and vast. It becomes luminous not by raising its temperature but by expanding its surface. It is no longer a quiet main-sequence star. It is bloated, unstable, nearing the end. For lower mass stars, those similar to or smaller than the Sun, this is the final phase of grandeur. The core, composed of helium, contracts further. When the temperature crosses 100 million Kelvin, helium ignites in a flash. Not an explosion, but a rapid runaway fusion event. Helium fuses into carbon and oxygen. The flash stabilizes the core for a time. A new balance is struck. The red giant stabilizes, if only briefly. The envelope is now tenuous. A strong stellar wind builds, driven by both radiation and pressure. The star begins to shed its outer layers. Shells of gas drift away into space, lit by the remaining core like lanterns in mist. What remains is a white dwarf, a naked core, hot and small, about the size of Earth. It no longer burns fuel. It merely cools, radiating away the last heat of its long life. The white dwarf is dense. A teaspoon of it would weigh tons. And yet it shines, dimly, for billions of years. The sun will become such a relic. In 5 billion years, our star will cast off its atmosphere and rest as a pale white ember, glowing faintly in the twilight of time. But for stars with greater mass, the ending is far more violent. They burn through hydrogen quickly, then helium, then heavier elements. The core becomes layered, like an onion, each shell fusing a different element. Carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. With each new fusion process, the temperature and pressure rise. But there is a limit. Iron is that limit. Fusing iron does not release energy. It consumes it. When the core fills with iron, the engine stalls. The outward pressure of radiation disappears. Nothing holds gravity back. Collapse begins. The core falls inward in milliseconds. Electrons are crushed into protons, forming neutrons. The matter becomes incompressible. The collapse halts abruptly, and the rebound sends a shockwave outward. In that instant, neutrinos, those ghost-like particles, pour out in vast numbers, carrying away energy. The shockwave, assisted by this sudden flood, tears through the star, blowing off its outer layers in a colossal detonation, a supernova. For a brief time, the star outshines its entire galaxy. A supernova near Earth would cast shadows at night. It would be as bright as the full moon. The explosion spreads heavy elements, carbon, oxygen, gold, uranium into space. These are the seeds of new stars, new planets, and eventually, new life. We are built from this wreckage. The iron in our blood, the calcium in our bones, the carbon in our cells, all forged in stellar death. What remains after such an explosion depends on the mass that was left behind. If the remnant is less than about 3 times the mass of the sun, the core stabilizes as a neutron star. Imagine a city-sized sphere, 10 kilometers across, denser than anything else in the universe apart from black holes. A thimble of neutron star matter would outweigh a mountain. The surface gravity is so immense that any object dropped from a centimeter above would strike with the force of a bomb. Neutron stars often spin rapidly, their magnetic fields sweeping through space. These rotating beacons are called pulsars. With each turn, they emit a pulse of radiation like the beam of a lighthouse. Some spin hundreds of times per second, a blur of dense matter trapped in an eternal twirl. But if the remnant is more massive still, not even neutron degeneracy pressure can halt the collapse. The core continues falling. There is no force in nature strong enough to stop it. The result is a black hole. This is not just an object. It is a boundary in space and time. Beyond the event horizon, nothing escapes, not light, not sound, not thought. The core collapses into a point of infinite density, a singularity. Around it, space is warped beyond comprehension. Time itself slows as you approach. To fall into a black hole is to vanish from the universe's visible story. your final light stretched and reddened until it fades into silence. Black holes do not roam freely, devouring stars at random. They obey gravity like any other mass. But when they do feed, the process is spectacular. Matter spirals inward, heating to millions of degrees, emitting X-rays and gamma rays. In some cases, vast jets erupt from the poles, carving cavities in the interstellar medium. The feeding is not quiet. It is theatrical, violent, luminous, beyond understanding. The star is gone. The fusion is over. But its legacy persists in the debris scattered across light years, in the elements scattered through future generations of stars, in the silent core that endures as neutron star or black hole. Every galaxy is shaped by such events. Every planet owes its material to the ghosts of long-dead suns. A star's life is long and quiet. Its death is brief and cataclysmic. And in that ending, the seeds of new worlds are born. In the darkness between the stars, clouds of gas drift silently, great volumes of hydrogen and helium, tinged with traces of heavier elements. For eons, they remain quiet, cold, featureless. But within these vast expanses, gravity begins its slow, relentless whisper. Slight imbalances, perhaps triggered by a passing shockwave from an ancient supernova or the subtle tug of a neighboring cloud, set particles into motion. Denser regions collapse inward, drawing in more mass. The process accelerates. The cloud fragments. Each fragment forms a rotating globule, an embryo of a future star. These protostars, cloaked in veils of dust, cannot yet be seen in visible light. They glow faintly in infrared, heat building as gravity compresses their hearts. The core tightens, pressure climbs, temperature rises. But for millions of years, there is no fusion. The heat is gravitational, a furnace built on falling. As the protostar contracts, it begins to spin faster. This is not by choice, but by law. Angular momentum conserved as mass collapses. The spinning disk around the protostar flattens and spreads, forming the stage for the next act, the birth of planets. Within the disk, dust grains coalesce. Minute collisions build larger clumps. The game is not fair. The biggest grow faster, drawing in smaller bodies. What begins as scattered dust becomes a chaos of tumbling rock and ice, each fragment following its own orbit, some spiraling inward, others flung outward. Over time, gravitational dance favors the few. Planetary embryos emerge, planetesimals the size of mountains, then continents. Some collide and shatter, others merge. Those that endure become protoplanets, their paths more circular, their mass sufficient to shape themselves into spheres. Gas giants form farther out, where cold temperatures allow volatile gases to condense. These massive worlds draw in hydrogen and helium, growing rapidly, their cores cloaked in deep atmospheres, closer to the star, where heat drives gases away. Terrestrial planets remain barren, rocky, fragile. In the heart of the system, the protostar finally reaches the threshold. Its core crosses 10 million Kelvin. Hydrogen ignites. Fusion begins. A balance is struck, the inward pull of gravity matched by the outward push of energy. The star is born. The sun awakens. Its fierce light sweeps away the remnants of the gaseous cloud, pushing back against the birth materials that formed it. The radiation and solar wind clear out debris, shaping the remaining architecture of the system. The planets that survive do so at the whim of this stellar tantrum, and their fate is sealed in the geometry of their orbits. In the early chaos, impacts are frequent. The inner solar system becomes a battlefield. Asteroids and comets bombard the young Earth. Some bring water, others sterilize the surface with fire. The scars remain in cratered moons, in tilted axes, in odd orbital resonances. A late, great impact tears a chunk from Earth's side. The debris coalesces into a satellite, the Moon. Its presence stabilizes Earth's rotation, sets tides in motion. and locks our planet into a rhythm that will nurture future life. After a few 100 million years, the bombardment slows, the solar system settles, the planets spin quietly in their orbits, moons circle planets, and the sun shines with steady brilliance. But the sun is not still. Its surface roils with convection. Magnetic storms arc into space. The solar wind continues, an eternal gale of charged particles streaming outward, touching every planet and pressing against the interstellar void. The sun's light takes 8 minutes to reach Earth. The signals we receive from its surface are already history. What we see is not what is, it is what was. This delay in light is not unique to our star. It is the universal consequence of speed and distance. Every point in the sky is a museum of the past. The farther we look, the older the image. A galaxy 10 million light-years away appears as it was 10 million years ago. We are surrounded not by objects in the present, but by echoes, fossils of light. Distance and time are entwined. To observe deeply is to peer into history. A telescope is a time machine, and the night sky is a window into moments that have long since passed. The nearest stars are light years away. Their parallax, the slight shift in apparent position as Earth moves around the sun, gives us a measure of their distance. Beyond a few hundred light years, even this shift is imperceptible. We must rely on luminosity, color, and spectral fingerprint to guess their remoteness. The stars themselves vary immensely. Some are red dwarfs, dim and enduring, destined to burn for trillions of years. Others are massive blue giants, burning so hot and fast they perish within a few million years. Most stars, like the sun, are main sequence a band on the Hertzsprung-Russell diagram that reveals a simple truth: a star's mass determines its fate. The diagram itself is no mere chart. It is a map of stellar life, from the dim and cool to the hot and brilliant. It lays out the stellar population in patterns that hint at hidden laws. The main sequence, the red giants, the white dwarfs, each region tells a story, not just of temperature and brightness, but of origin and destiny. The stars are not randomly placed. They cluster, drift in families, rotate around galactic centers. Many are not solitary. Binary systems are common: two stars locked in orbit, some distant, others so close they transfer mass, their evolution intertwined. Some binaries merge, igniting new flares of energy. Others erupt in nova or end in shared collapse. In rare cases, one devours the other. Their stories are many. Their silence conceals the violence beneath. What we call a star is a process, not a product. A balance of forces, a furnace of nuclear fire, a beacon that writes its own biography in light. Each flicker across the night sky is a whisper from a distant forge, a statement of physics, chance, and endurance. And each of these whispers arrives late, trailing behind the moment of its making, forever separated from the now by the span of space and time. Inside the quiet skeleton of a dying star, the fire of creation meets its limits. Hydrogen, once abundant and obedient, is long gone from the core. Helium, too, has fused into heavier elements: carbon, oxygen, silicon. What remains is a complex, layered relic, like an onion of atomic ancestry, each shell burning a different fuel, each closer to collapse than the last. The fusion reactions, which once staved off gravity, now accelerate with desperation. In the final days, a massive star can burn through silicon in mere hours, producing iron, a dead end in nuclear alchemy. Iron neither gives nor takes energy through fusion. It is inert, the ash of the stellar flame. The core grows heavy with it. Its weight, no longer countered by outward pressure, begins to pull inward. Faster than sound can escape, faster than the atom can respond. The iron heart collapses. Electrons slam into protons, forming neutrons. In an instant, a city-sized core becomes a neutron star. Above it, layers of gas fall inward like a city crushed by gravity. But the core resists. The infall halts, rebounds, An enormous shockwave bursts outward, ignited by a flood of neutrinos, the ghost particles of the universe pouring from the newborn neutron core in numbers beyond comprehension. The star explodes. A supernova lights the galaxy, outshining billions of suns. Its brilliance lasts only weeks, but in that moment, it sears itself into the cosmos, the elements forged in its interior gold. Uranium, iodine scatter into space. Dust enriched by the dead becomes the seeds of the living. The remnants of the star vary by mass. If the core is under the limit about 3 times the sun's mass, it settles as a neutron star. A thimbleful of its matter outweighs mountains. Its magnetic field is 1 trillion times stronger than Earth's. It may rotate hundreds of times per second, sending pulses of radiation across space, a lighthouse in the void. We call them pulsars, these trembling fossils. They speak not in words, but in timing perfect, mechanical, mournful. Each beat carries memory. Each signal is the echo of collapse held in exquisite rhythm. But if the core is heavier still, even neutrons are crushed. Nothing can resist the final fall. Space itself curves inward. Light cannot escape, and the star becomes invisible, a black hole. This term, so soft in sound, masks what it means. A black hole is not a thing, but a boundary. A cliff in space-time beyond which no return is possible. It is a wound in the structure of reality, the place where time stops making sense. Surrounding the black hole is the event horizon, the point of no return. Outside it, time moves forward. Inside, all futures lead to the singularity, a place where density becomes infinite and physics loses its voice. We do not know what lies at the singularity. Our equations scream with infinities and contradictions. General relativity bends. Quantum mechanics fractures. It is the edge of knowledge, the end of prediction. Black holes grow by swallowing. They devour stars, gas clouds, other black holes. At galactic centers, they sit like monarchs, invisible yet ruling. Some weigh millions or billions of solar masses. Their gravity sculpts the movement of stars, shapes galaxies, triggers jets of matter and energy that stretch across intergalactic space. They are silent architects of cosmic order, formed in violence, living in shadow. And yet, not all end in collapse. Lesser stars walk gentler paths. If born with low mass, they shine steadily for tens of billions of years, fusing hydrogen slowly, living longer than the current age of the universe. When their hydrogen is gone, they swell into red giants, shed their outer layers into space, and settle as white dwarfs. These stellar embers, roughly Earth-sized, glow faintly for eons. Some may eventually cool into black dwarfs. Though the universe is still too young to have produced any, they are the final breath of stars too small to die with thunder. In some binary systems, white dwarfs steal matter from a companion. When enough accumulates, a thermonuclear runaway occurs. The star explodes in a Type Ia supernova so consistent in brightness that it serves as a cosmic milepost, measuring the universe's expansion. There are other signals of distance, too. Cepheid variables, massive stars that pulse rhythmically, grow brighter and dimmer over predictable cycles. Their period tells us their true luminosity. Comparing this to their apparent brightness reveals how far away they are. Light, again, is the courier of truth. Our knowledge of the universe is built from what arrives on waves of light and particles of ghostly origin. Neutrinos from supernovae, gravitational ripples from colliding black holes, shadows cast by galaxies, spectra of starlight. Even the silent vacuum speaks. The cosmic microwave background relic radiation from the birth of the universe saturates space. A whisper from 13 billion years ago. Its pattern tells us the shape of space, the fate of time, the balance of matter and dark energy. And so we orbit, this Earth spinning beneath a star that will someday swell, burn its hydrogen to helium, shed its skin, and leave behind a white dwarf. Long after we are gone, it will remain, dimming slowly. Around it may still circle the ghost of what was a system shaped by violence and decay, but also by balance, emergence, and radiance. The universe, for all its harshness, is not a place of pure entropy. It is a realm where structure can rise from chaos, where time does not just erode but reveals. Every star carries a story written in heat and pressure, forged in collapse and light. Every planet is a testimony to improbable assembly, a relic of gravitational games. And every life that gazes skyward becomes part of this unfolding epic, finite, fragile, yet curiously aware of the infinite beyond. In the cold spaces between galaxies, in the dark hearts of dying stars, in the minute reactions of subatomic particles, there are echoes, not just of matter and energy, but of questions, of silence interrupted by light, of time made visible. The story never ends. It only fades beyond the horizon, into the vastness from which it came.
2.5 million light-years away. A galaxy 4 times larger than our own is racing toward us at 250,000 miles per hour. The Andromeda Galaxy contains 1 trillion stars, countless worlds, and mysteries that challenge everything we thought we knew about the universe. Today we witness stellar nurseries where baby stars are born in cosmic violence, explore planets where diamonds rain from methane skies, and encounter black holes so massive they could swallow our entire solar system in seconds. Our journey takes us through cosmic storms, past gravitational whirlpools, toward civilizations that might have risen and fallen a billion years before Earth even existed. Prepare yourselves. We begin. Our spacecraft engines ignite with the power of 1,000 suns as we break free from Earth's gravitational embrace. The blue marble that has been humanity's home for millions of years shrinks to a pale dot behind us, a single pixel of collective memory, then disappears entirely into the cosmic darkness. We are now truly alone in the void, beginning the longest journey any conscious being has ever attempted. The first challenge hits us immediately, not as a physical threat, but as a conceptual weight, the sheer scale of what we are attempting. To reach Andromeda, we must travel a distance so vast that light itself, moving at 186,000 miles per second, takes 2.5 million years to make this journey. If we could drive there in a car at highway speeds, never stopping, never sleeping, it would take us 30 billion years. The dinosaurs would still be ruling Earth when we finally arrived, and our own sun would have long since died. But we have technology beyond current human imagination. Our vessel bends space and time around itself, creating a bubble of warped reality that allows us to slip between the normal rules of physics. We accelerate not through space, but through the fabric of space-time itself. The stars around us begin to shift and blur, their light bending into chromatic arcs as we approach speeds that would have been impossible just moments before. This is not about brute force. It is about finding a loophole in the laws of nature, a way to fold the map instead of walking across it. As we leave our solar system behind, we pass through the Kuiper Belt, where ancient chunks of ice and rock drift in eternal darkness. These are the leftover building blocks of our solar system, frozen in time for 4.5 billion years, silent witnesses to the birth of our world. Pluto, once considered our 9th planet, appears as a lonely sentinel guarding the edge of everything we have ever known. Its heart-shaped glacier a fragile, frozen farewell. Beyond Pluto lies the Oort cloud, a spherical shell of icy objects that extends nearly a light-year from our sun. This is where comets are born, in the frigid depths where temperatures drop to just a few degrees above absolute zero. It is not a belt, but a ghostly sphere, a halo of potential worlds and frozen water that marks the true gravitational boundary of our solar system. We are entering a region where the sun's influence barely reaches, where the space between objects is so vast that a collision is nearly impossible. The nearest star to our sun, Proxima Centauri, glows like a red ember in the distance. It would take a conventional spacecraft over 70,000 years to reach it. But we pass it in what feels like minutes. Its faint, angry light a fleeting reminder of another star's quiet story. We are now in interstellar space, the vast emptiness between star systems, where matter is so sparse that you could travel for millions of miles without encountering a single atom. This is where most space travelers would feel the crushing weight of isolation, the profound loneliness of being adrift in an ocean of nothingness. But we push forward with purpose. The Andromeda Galaxy beckons from across the cosmic ocean, its spiral arms slowly rotating in a dance that has continued for billions of years. We are no longer bound by the limitations of our species or our world. We are explorers of the infinite, and our destination contains wonders that will challenge every assumption we have ever made about reality itself. The real journey is just beginning. We enter the local void, a region of space so empty it defies comprehension. Here, between the galaxy clusters, matter exists in concentration so low that an entire cubic meter of space might contain only a single atom. The temperature drops to just a few degrees above absolute zero, and the only light comes from distant galaxies billions of light years away, their ancient photons stretched and tired from their long journey. This is cosmic loneliness on a scale that breaks human understanding. If Earth were placed in the center of this void, our night sky would be completely black, except for the faint glow of the Milky Way itself. No other galaxies would be visible to the naked eye. Ancient civilizations would have developed entirely different mythologies, religions, and scientific theories about the universe. Based on this profound isolation, they would have seen a universe with only one galaxy, one island of light in an infinite sea of darkness, and perhaps concluded that they were the center of all creation, a singular miracle in an empty cosmos. But the void is not truly empty. Dark matter, the mysterious substance that makes up 85% of all matter in the universe, forms invisible scaffolding throughout this region. We cannot see it directly, but its gravitational influence shapes the very fabric of space-time around us. Our instruments detect its presence through subtle variations in the cosmic microwave background radiation, the afterglow of the Big Bang itself. It is the ghost in the machine, the silent architect of cosmic structure, holding galaxies together and guiding their dance across billions of years. It is the unseen river that carves the canyon of the cosmos. As we travel deeper into the void, we encounter something unexpected: rogue planets, ejected from their home solar systems by gravitational interactions with passing stars. These orphaned worlds drift through the darkness, no longer warmed by any sun. Their surfaces frozen solid, and their atmospheres collapsed into ice. Some of these planets are larger than Jupiter, others smaller than Earth, but all share the same fate of eternal wandering through the cosmic deep. One rogue planet we encounter tells a particularly haunting story. Its surface shows evidence of ancient oceans, now frozen kilometers thick. Beneath that ice, our scanners detect something remarkable: a subsurface ocean, kept liquid by the planet's own radioactive decay and tidal forces from a long-lost moon. In this hidden sea, completely isolated from any star's light, primitive life forms might still exist, evolved from organisms that survived their world's ejection into space billions of years ago. They would be creatures of darkness and pressure, their biology powered not by sunlight, but by chemical reactions in the planet's core. A civilization of beings who have never seen a star, whose concept of the universe is a dark, warm ocean, and for whom the idea of an outside would be pure fantasy. The void also contains the remnants of ancient galaxy collisions, tidal streams of stars, stretched across millions of light years, mark the paths where smaller galaxies were torn apart by the gravity of larger ones. These stellar graveyards tell the violent history of cosmic evolution, where galaxy clusters grow by cannibalizing their smaller neighbors in a process that continues to this day. We pass through regions where the cosmic web itself is visible, vast filaments of dark matter and ordinary matter that connect galaxy clusters across hundreds of millions of light years. These structures formed in the early universe, when matter first began to clump together under the influence of gravity. They are the highways along which galaxies travel, the channels through which matter flows from one region of the universe to another. The silence here is absolute, broken only by the faint whisper of cosmic rays. High-energy particles traveling at nearly the speed of light, accelerated by unknown processes in the violent hearts of distant galaxies. These particles are the ghosts of ancient explosions, messengers from a more violent time, and they are the only sound in this vast, empty cathedral. Something magnificent appears in the distance, a faint, diffuse glow that slowly resolves into a city of light. A galaxy cluster, containing hundreds of individual galaxies, each one an island universe in its own right. The Virgo cluster spans 13 million light-years across space, containing more than 300 galaxies bound together by gravity in a cosmic dance that has continued for billions of years. As we approach this stellar metropolis, the scale becomes overwhelming. Each galaxy contains hundreds of billions of stars, and many of these galaxies are larger than our own Milky Way. Some are elegant spirals with arms that sweep through space like frozen fireworks. Others are massive ellipticals that glow with the combined light of 1 trillion ancient suns, their reddish hue a sign of their advanced age. And still others are irregular dwarfs, twisted and distorted by the gravitational pull of their larger neighbors, their stars scattered like dust in the wind. The largest galaxy in the cluster, Messier 87, dominates the central region like a cosmic giant. This massive elliptical galaxy contains over 1 trillion stars and harbors one of the most powerful black holes ever discovered. The black hole at its center is so massive that it contains the equivalent of 6.5 billion suns, a gravitational singularity that has consumed entire star systems for breakfast. And it is actively feeding on surrounding matter, creating jets of plasma that shoot out from its poles at nearly the speed of light. These jets extend for thousands of light years, creating a cosmic lighthouse that can be seen from billions of light years away. The energy released by matter falling into this black hole is so enormous that it heats the surrounding gas to millions of degrees, creating a hot, glowing atmosphere that pervades the entire galaxy cluster, a celestial bonfire that sterilizes any potential life for light years around. Between the galaxies, we discover an invisible ocean of superheated gas, heated to temperatures of 50 million degrees Celsius by the gravitational energy of the cluster itself. This intergalactic medium contains more matter than all the stars in all the galaxies combined. Yet, it is so diffuse that it is completely invisible to the naked eye. Only our most sensitive instruments can detect its presence through the X-rays it emits as it radiates away its enormous heat. The cluster is also filled with dark matter, which makes up about 85% of all the matter here. This mysterious substance forms an invisible scaffolding that holds the entire cluster together, preventing the galaxies from flying apart despite their enormous speeds. Some galaxies are moving through the cluster at over 1,000 kilometers per second, fast enough to travel from Earth to the Moon in just 6 minutes. Yet they are trapped in this gravitational web, destined to orbit for eternity. As we navigate through this cosmic city, We witness ongoing galactic interactions. Smaller galaxies are being torn apart by tidal forces, their stars stripped away to form long streamers that will eventually be absorbed by larger galaxies. This is galactic cannibalism on a massive scale, where the strong devour the weak in a process that has shaped the evolution of galaxies since the early universe. The gravitational forces here are so intense that they bend light itself, creating gravitational lenses that magnify and distort the images of even more distant galaxies lying behind the cluster, giving us a warped, fisheye view of the deeper cosmos. We witness something extraordinary: two galaxies locked in a gravitational death spiral, their collision unfolding over hundreds of millions of years. The antennae galaxies, once separate and distinct spiral galaxies, are now merging in a cosmic catastrophe that will reshape both systems completely. Their spiral arms have been stretched and distorted into long tidal tails that extend for hundreds of thousands of light years, resembling the antennae of a cosmic insect. The collision zone is a stellar nursery of unprecedented violence. Gas clouds from both galaxies are smashing together at speeds of hundreds of kilometers per second, compressing and heating the interstellar medium until it reaches temperatures where new stars can form. The rate of star formation here is 10 times higher than in normal galaxies, creating brilliant clusters of young, hot stars that burn with the intensity of blue-white diamonds. But star formation is not the only consequence of this cosmic collision. The gravitational chaos is also feeding the supermassive black holes at the centers of both galaxies. As gas spirals inward toward these cosmic monsters, it heats up and glows with X-ray radiation, creating some of the brightest objects in the universe. These active galactic nuclei pump enormous amounts of energy into their surroundings, creating jets of plasma that extend far beyond the visible galaxies themselves. The merger is also creating something entirely new: globular clusters, dense balls of stars that will survive long after the collision is complete. These stellar cities contain hundreds of thousands of stars packed into regions just a few dozen light years across. They are among the oldest objects in the universe, and new ones are being born in the chaos of this galactic collision. As we watch this cosmic catastrophe unfold, we realize we are seeing the future of our own galaxy. In approximately 4 billion years, the Milky Way will collide with the Andromeda Galaxy in a similar cosmic dance. The collision will take place over hundreds of millions of years, gradually reshaping both galaxies into something entirely new. A giant elliptical galaxy that will dominate the local group. The space between the colliding galaxies is not empty. It is filled with streams of stars that have been torn from their home galaxies by tidal forces. These stellar refugees will wander through intergalactic space for billions of years, no longer bound to any particular galaxy. Some will eventually be captured by other galaxies, while others will drift alone through the cosmic void forever. Their light a faint, lonely echo of a home they can never return to. Despite the apparent violence of the collision, individual stars rarely collide with each other. The distances between stars are so vast that most will simply be redistributed into new orbits around the merged galaxy's center. However, many planetary systems will be disrupted, their planets flung into new orbits or ejected from their home systems entirely, sent on a one-way journey into the cold, dark void. The collision is also creating something beautiful: shock waves that compress the interstellar medium and cause it to glow with brilliant colors. These cosmic fireworks paint the merger zone in shades of red, blue, and green, creating one of the most spectacular sights in the universe. A testament to the fact that even in destruction, there is a kind of terrible, awe-inspiring beauty. We encounter our first truly alien world, a planet orbiting a binary star system where the very nature of day and night challenges everything we thought we knew about planetary environments. This world, twice the size of Earth, experiences a complex cycle of illumination as it orbits two stars locked in their own gravitational dance. The primary star is a yellow dwarf, similar to our Sun. But its companion is a red dwarf that burns with a cooler, dimmer light, a crimson eye in the sky. As the planet moves through its orbit, it experiences periods of single-star days, double-star days, and even brief, breathtaking eclipses when one star passes in front of the other. The result is a world where the concept of a standard day has no meaning, where the inhabitants must adapt to constantly changing patterns of light and darkness. The sky here is never truly dark, but shifts from a bright golden yellow to a deep blood-red twilight, a perpetual state of dawn or dusk. The planet's surface reflects this chaotic illumination cycle. Vast regions are covered in crystalline formations that act like natural solar collectors, gathering and storing light energy during the brightest periods and releasing it slowly during the darker phases. These crystal forests create a landscape that shimmers and glows with accumulated starlight, painting the world in constantly shifting colors, a living kaleidoscope that breathes light. The atmosphere here is unlike anything in our solar system. It contains high concentrations of noble gases that create spectacular auroras when charged particles from the binary stars interact with the planetary magnetic field. These auroras are not confined to the polar regions like on Earth. They dance across the entire sky in ribbons of green, purple, and gold that can be seen even during the day. A constant, silent celestial ballet. Life on this world has evolved in remarkable ways. The dominant species are silicon-based organisms that incorporate the planet's crystals into their biological structures. They can photosynthesize using light from both stars simultaneously, making them incredibly efficient at converting stellar energy into biological energy. During the double star periods, they grow rapidly, storing excess energy in specialized organs. During the darker periods, they enter a state of reduced activity, living off their stored energy reserves, their crystalline bodies glowing faintly in the dim red light of the smaller star. The planet's oceans are equally extraordinary. They contain dissolved minerals that make the waters slightly luminescent, creating seas that glow with their own internal light. Underwater, entire ecosystems have evolved around chemosynthetic organisms that derive energy from the planet's geological activity rather than from starlight. These deep-sea communities exist in complete independence from the surface world, thriving in eternal darkness beneath the glowing waters. A hidden biosphere that has never known the touch of a sun. The binary star system itself is evolving. The two stars are slowly spiraling inward toward each other, their orbital decay caused by the emission of gravitational waves. In approximately 2 billion years, they will merge in a spectacular collision that will briefly outshine entire galaxies. When that happens, this remarkable world will be vaporized in seconds, its complex ecosystems and beautiful crystal landscapes reduced to their component atoms. But for now, the planet continues its complex dance around its twin suns, a testament to the incredible diversity of worlds that exist in the universe. As we leave this system behind, we carry with us the knowledge that life finds ways to adapt to conditions that would seem impossible to Earth-based organisms, and that the universe is far more imaginative in its creations than we could have ever dreamed. We approach a stellar graveyard, where the remnants of dead stars create one of the most dangerous regions in the galaxy. Here, neutron stars, The collapsed cores of massive stars that exploded as supernova spin at incredible speeds while generating magnetic fields trillions of times stronger than Earth's. One neutron star captures our attention immediately. It is only 20 kilometers across, smaller than most cities. Yet it contains more mass than our entire sun. A single teaspoon of neutron star material would weigh 6 billion tons on Earth. The gravity here is so intense that the escape velocity is nearly half the speed of light. And time itself runs noticeably slower than in normal space. This particular neutron star is a pulsar, spinning 30 times per second while beaming lighthouse-like streams of radiation from its magnetic poles. Each pulse arrives with clockwork precision, more accurate than the most precise atomic clocks humans have ever built. The beams sweep across space like the rotating beam of a lighthouse, and when they point in our direction, our instruments detect bursts of radio waves, X-rays, and gamma rays. The space around the pulsar is filled with a wind of charged particles accelerated to nearly the speed of light. This pulsar wind creates a bubble of high-energy plasma that extends for light years in all directions, heating the surrounding interstellar medium to millions of degrees and creating a glowing nebula that can be seen from thousands of light years away. As we maintain a safe distance, we observe the pulsar's incredible power. In just 1 second, it releases more energy than our sun produces in an entire month. This energy comes from the neutron star's rotation. It is literally spinning down, converting its rotational energy into the radiation that we detect as pulses over millions of years. The pulsar will gradually slow down until it becomes a quiet, dark neutron star, invisible except for its gravitational effects. Near the pulsar, we encounter something even more exotic, a magnetar. A neutron star with a magnetic field so strong that it defies comprehension. The magnetic field here is a quadrillion times stronger than Earth's magnetic field, powerful enough to strip electrons from atoms at a distance of 1,000 kilometers. If you could somehow survive getting within 1,000 kilometers of a magnetar, the magnetic field would distort your atoms, stretching them into thin, needle-like shapes aligned with the field lines. Magnetars are rare and unstable. They occasionally experience starquakes, sudden rearrangements of their crystalline crusts that release more energy in 1/10 of a second than our sun produces in a year. These starquakes create bursts of gamma rays so intense that they can affect Earth's atmosphere from thousands of light years away. The region also contains isolated black holes, stellar corpses so dense that nothing, not even light, can escape their gravitational pull. These invisible monsters can only be detected by their gravitational effects on nearby matter, creating accretion disks of superheated gas that spiral inward while glowing with X-ray radiation. This is where massive stars come to die, creating some of the most extreme environments in the universe. A cosmic cemetery where the laws of physics are pushed to their absolute limits. We enter a region where space itself seems to be boiling with energy. Here, the fabric of space-time is constantly fluctuating with quantum foam, virtual particles that pop into existence and annihilate each other in time frames so brief that they seem to violate the conservation of energy. This is the quantum vacuum, and it is anything but empty. At the smallest scales, space and time become grainy and uncertain. The smooth fabric of space-time that we experience in everyday life breaks down into a churning sea of quantum fluctuations. Virtual photons, electron-positron pairs, and other exotic particles constantly appear and disappear, borrowing energy from the vacuum itself and paying it back before the universe notices the debt. These quantum fluctuations have real, measurable effects. They create a subtle force called the Casimir effect. where two parallel plates placed very close together in a vacuum will experience an attractive force due to the quantum fluctuations of the electromagnetic field. The space between the plates contains slightly fewer virtual photons than the space outside, creating a pressure difference that pushes the plates together. As we travel deeper into this quantum realm, we encounter something extraordinary, a region where the expansion of the universe itself is accelerating. Dark energy, the mysterious force that makes up 70% of all energy in the universe, is stretching space itself at an ever-increasing rate. This cosmic acceleration means that distant galaxies are moving away from us faster and faster, and eventually, they will recede so quickly that their light will never reach us. The nature of dark energy remains one of the greatest mysteries in cosmology. It might be a property of space itself, a quantum field that permeates all of reality, or something even more exotic that we do not yet understand. What we do know is that it is winning the cosmic battle against gravity, driving the universe toward a cold, dark future, where galaxies will be isolated islands in an ever-expanding sea of emptiness. In this region, we also encounter cosmic strings, theoretical one-dimensional defects in space-time that might have formed during the first moments after the Big Bang. These cosmic strings are thinner than a proton, but can stretch across entire galaxies, containing enormous amounts of energy and creating gravitational effects that can bend light and distort space around them. If cosmic strings exist, they would be among the most exotic objects in the universe. They would vibrate like guitar strings, creating gravitational waves that could be detected by future generations of instruments. Some theories suggest that cosmic strings could even be used as cosmic highways, allowing advanced civilizations to travel vast distances by following the strings through space. The quantum vacuum also contains the possibility of spontaneous symmetry breaking, where the fundamental forces of nature might suddenly change their properties. This could create bubble universes with different physical laws, where the speed of light, the strength of gravity, or even the number of spatial dimensions might be different from our own universe. Here, at the intersection of quantum mechanics and cosmology, we glimpse the deepest mysteries of existence itself. A place where the rules of reality are not fixed, but fluid, and where anything seems possible. We discover a cosmic phenomenon that challenges our understanding of physics itself. A region where time flows differently due to extreme gravitational fields. Here, the curvature of space-time is so severe that hours pass like minutes, and the very concept of simultaneity breaks down completely. The source of this temporal distortion is a rotating black hole of intermediate mass, spinning so rapidly that it drags space-time around with it like honey. This effect, called frame dragging, creates a region where it is impossible to remain stationary relative to distant stars. Everything in the vicinity is forced to rotate along with the black hole, caught in a cosmic whirlpool of twisted space-time. As we approach the ergosphere, the region outside the black hole's event horizon where space-time is being dragged around, we experience something unprecedented. Our clocks begin to run slow compared to the time we left behind. Minutes stretch into hours, and hours into days. If we were to spend just 1 hour in the deepest part of the ergosphere, decades would pass in the outside universe. We would return to a future we never lived, a ghost in our own timeline. The black hole itself is a monster, containing the mass of 10,000 suns compressed into a region smaller than a city. Its event horizon, the point of no return, appears as a perfect sphere of absolute blackness, surrounded by a swirling disk of superheated matter that glows with the intensity of 1 billion stars. This accretion disk is where matter spirals inward toward its doom, heating up to temperatures of millions of degrees as it falls toward the black hole. But the most remarkable feature of this system is the jets of plasma that shoot out from the black hole's poles at 99% the speed of light. These relativistic jets extend for thousands of light years, creating cosmic beacons that can be seen from across the universe. The energy for these jets comes from the black hole's rotation itself, through a process that extracts energy from the spinning space-time around the black hole. Near the black hole, we encounter something that should not exist according to our current understanding of physics matter that appears to be falling upward, away from the black hole's gravity. This is an illusion created by the extreme curvature of space-time, where the very concepts of up and down lose their meaning. What we are seeing is matter following geodesics, the straightest possible paths through curved space-time that appear curved to our outside perspective. The gravitational field here is so strong that it creates multiple images of distant objects through gravitational lensing. Stars behind the black hole appear as rings of light, their images distorted and magnified by the black hole's gravity. We can see the same star from multiple angles simultaneously, as light from the star follows different paths around the black hole to reach us. In this region, the fundamental nature of space and time becomes apparent. They are not separate entities, but part of a single, unified space-time fabric that can be stretched, compressed, and twisted by the presence of matter and energy. The black hole is not just an object in space. It is a wound in the fabric of reality itself, a place where our understanding of the universe breaks down completely. We encounter the most beautiful and terrifying sight in the universe, a star in the process of dying, its outer layers being blown away in a spectacular planetary nebula that paints space in brilliant colors. The dying star, a white dwarf no larger than Earth but containing the mass of our sun, sits at the center of an expanding shell of glowing gas that stretches for light years in all directions. The nebula itself is a masterpiece of cosmic art. Shells of different gases glow in distinct colors: hydrogen in red, oxygen in green and blue, nitrogen in deep red, creating intricate patterns that resemble flowers, butterflies, or abstract sculptures. These colors are created by the intense ultraviolet radiation from the white dwarf, which ionizes the surrounding gas and causes it to fluoresce like a cosmic neon sign. The white dwarf at the center is the exposed core of what was once a star, similar to our sun. For billions of years, it burned hydrogen and helium in its core, maintaining a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. But eventually, the fuel ran out, and the star began its death throes. As the nuclear fires died down, gravity began to win the battle. The star's core collapsed, while its outer layers expanded, creating a red giant that was hundreds of times larger than the original star. For millions of years, the red giant pulsed and varied in brightness, shedding its outer layers in a series of stellar winds that created the beautiful nebula we see today. The white dwarf itself is an object of incredible density. A cubic centimeter of white dwarf material would weigh as much as a car on Earth. The surface gravity is so intense that a person standing on a white dwarf would weigh about 1,000,000 times more than they do on Earth. The surface temperature is over 50,000 degrees Celsius, hot enough to ionize any material that comes near it. But this white dwarf is not alone. It has a companion star, a red dwarf that orbits close enough to have matter stripped away by the white dwarf's gravity. This stolen matter spirals inward, forming an accretion disk that glows with X-ray radiation. Periodically, enough matter accumulates on the white dwarf's surface to trigger a thermonuclear explosion, a nova that can briefly outshine entire galaxies. A final violent burst of light from a dying star. The nebula is also a recycling plant for the universe. The gas being expelled contains heavy elements forged in the dying star's core: carbon, nitrogen, oxygen, and other elements essential for life. These elements will eventually be incorporated into new stars and planets, continuing the cosmic cycle of death and rebirth that has been ongoing since the first stars formed billions of years ago. As we watch this stellar death unfold, we are witnessing the fate that awaits our own sun. In about 5 billion years, the sun will expand into a red giant, engulfing the inner planets before finally shedding its outer layers and leaving behind a white dwarf surrounded by a planetary nebula that will glow for thousands of years. A final, beautiful monument to a star that once gave life. We drift into a region where space itself becomes a lens, bending and focusing light from distant galaxies through the sheer power of gravity. Here, a massive galaxy cluster acts as a cosmic magnifying glass, its immense gravitational field warping space-time so severely that it creates multiple, distorted images of the same background galaxies, stretched into glowing arcs that paint the darkness with impossible geometry. The cluster contains over 1,000 galaxies, each one an island universe in its own right, bound together by the invisible grip of dark matter. But it is not the visible galaxies that create the lensing effect. It is the dark matter halo that surrounds them. A massive concentration of invisible matter that outweighs all the visible stars and gas by a factor of 10 to 1. As light from distant galaxies travels toward us, it must pass through the curved space-time created by the cluster's enormous mass. The light follows the straightest possible path through this curved space. But from our perspective, these straight paths appear curved, creating the spectacular arcs and rings we observe. Some background galaxies appear as complete Einstein rings, perfect circles of light that surround the lensing cluster like cosmic halos. The gravitational lensing effect is so powerful that it allows us to see galaxies that would otherwise be completely invisible. The cluster's gravity magnifies the light from these distant galaxies by factors of 10, 50, or even 100, making them appear brighter and larger than they actually are. This cosmic telescope effect lets us observe galaxies as they existed when the universe was less than 1 billion years old, providing a window into the early stages of cosmic evolution. One particularly spectacular lensed galaxy appears as a giant arc stretched across half the sky. This galaxy is so distant that its light has traveled for over 12 billion years to reach us, showing us what galaxy formation looked like when the universe was in its infancy. The galaxy appears distorted and fragmented, broken into multiple images by the complex gravitational field of the cluster. The lensing effect also reveals the true distribution of matter in the cluster. By measuring how the background galaxies are distorted, we can map the invisible dark matter that dominates the cluster's mass. This dark matter mapping shows that the cluster is not a single, uniform structure, but rather a complex web of dark matter clumps and filaments that stretches across millions of light years. The cluster itself is a violent place. Galaxies are constantly colliding and merging, their stars scattered and their gas stripped away by the hot, dense medium that fills the space between galaxies. This intergalactic medium is heated to temperatures of over 50 million degrees by the gravitational energy of the cluster, creating a vast atmosphere of X-ray emitting plasma. The cluster is also home to some of the most massive black holes in the universe. At the center of the dominant galaxy, a supermassive black hole containing billions of solar masses is actively feeding on the surrounding gas, creating jets of plasma that extend for hundreds of thousands of light years and heat the cluster's atmosphere. This is gravity as a cosmic architect, shaping the very fabric of space-time and creating natural telescopes that reveal the deepest secrets of the universe. A silent, invisible force that paints the cosmos with light from a time before time. We witness the birth of something that should not exist according to our current understanding of physics, a primordial black hole. Formed not from the collapse of a massive star, but from the extreme density fluctuations that existed in the first moments after the Big Bang. This cosmic relic is a window into the very early universe, when the laws of physics were still being written and the fundamental forces were unified in ways we can barely comprehend. The primordial black hole is tiny compared to the stellar mass black holes we have encountered so far. It contains only the mass of a small asteroid, compressed into a region smaller than a proton. But its small size makes it incredibly exotic, with properties that bridge the gap between general relativity and quantum mechanics in ways that challenge our deepest theoretical understanding. According to quantum mechanics, the black hole should be evaporating through a process called Hawking radiation. The curved space-time around the black hole creates virtual particle pairs at the event horizon, and occasionally, one particle from each pair falls into the black hole while the other escapes. This process slowly reduces the black hole's mass, causing it to shrink and eventually disappear in a final burst of radiation. But this primordial black hole is behaving strangely. Instead of evaporating as theory predicts, it appears to be growing, accreting dark matter from its surroundings at a rate that exactly balances the mass loss from Hawking radiation. The black hole has reached a state of equilibrium, maintaining a constant mass while existing in a delicate balance between quantum evaporation and classical accretion. A cosmic stalemate between two of the universe's most powerful forces. The space around the black hole is a laboratory for extreme physics. The gravitational field is so intense that it creates measurable effects on the passage of time itself. Clocks near the black hole run slower than those in normal space, and the wavelength of light is stretched as it climbs out of the gravitational well. The black hole's accretion of dark matter creates a unique observational signature. As dark matter particles fall toward the event horizon, they interact with each other through processes that are normally too weak to detect. The extreme environment near the black hole amplifies these interactions, creating a faint glow of exotic particles that provides our first direct observation of dark matter's true nature. The primordial black hole also serves as a natural particle accelerator. The intense gravitational field accelerates in-falling matter to speeds approaching the speed of light, creating conditions that existed nowhere else in the universe since the first moments after the Big Bang. The collision of these high-energy particles recreates the physics of the early universe, providing insights into the fundamental nature of matter and energy. As we observe this cosmic relic, we realize that we are looking at a fragment of the universe's birth, a piece of the Big Bang that has survived for over 13 billion years. The black hole carries information about the conditions that existed when the universe was less than a second old, when the temperature was billions of degrees and the density was greater than that of atomic nuclei. This is cosmology in its purest form, where the smallest objects reveal the grandest truths about the nature of reality itself. We approach a cosmic phenomenon that exists at the very edge of possibility, a white hole, the theoretical opposite of a black hole, where matter and energy are expelled rather than consumed. If black holes are cosmic drains that swallow everything that comes near them, white holes are cosmic fountains that spew matter and energy into space at incredible rates. The white hole appears as a brilliant point of light that outshines entire star clusters, surrounded by expanding shells of matter moving at significant fractions of the speed of light. Unlike black holes, which have event horizons that trap everything inside. White holes have event horizons that prevent anything from entering. Matter and energy can only flow outward, creating a cosmic geyser that has been erupting for billions of years. The physics of white holes is even more exotic than that of black holes. According to general relativity, white holes are mathematically valid solutions to Einstein's field equations. But they violate the second law of thermodynamics by creating, rather than destroying information. They represent a reversal of time's arrow, where the normal flow of cause and effect is turned upside down. The white hole's origin is shrouded in mystery. One possibility is that it formed from the time-reversed collapse of a massive star, where instead of matter falling inward to create a black hole, matter exploded outward from a point of infinite density. Another theory suggests that white holes might be the exit points of black holes from other universes, connected through cosmic wormholes that allow matter to flow from one universe to another. The matter being expelled from the white hole is unlike anything we have seen before. It consists of exotic particles that do not exist under normal conditions, particles that carry negative energy, antimatter in configurations that should not be stable, and even hypothetical particles that exist only in the most advanced theoretical models. This matter creates an expanding bubble of space that glows with energy across the entire electromagnetic spectrum. The white hole's gravitational field is equally bizarre. While black holes curve space-time inward, creating gravitational wells that trap matter, white holes curve space-time outward, creating gravitational hills that repel matter. The closer you get to a white hole, the stronger the repulsive force becomes, making it impossible to approach the event horizon from the outside. The white hole is also a source of gravitational waves. But these waves are different from those produced by black hole mergers. Instead of the characteristic chirp of objects spiraling inward, white hole gravitational waves have a complex pattern that reflects the chaotic nature of matter being expelled at high speeds. These waves carry information about the interior structure of the white hole and the exotic physics that governs its behavior. The white hole's existence challenges our understanding of causality and the nature of time itself. If white holes can exist, then the universe might be far stranger than we imagine, with regions where time flows backward and effect precedes cause. The white hole represents a cosmic paradox, an object that should not exist according to our current understanding of physics. Yet, here it is, defying our expectations and forcing us to reconsider the fundamental laws of nature. This is where theoretical physics meets cosmic reality, where the impossible becomes possible in the extreme environments of the universe. We encounter a structure so vast that it challenges our understanding of what constitutes a single object in the universe, a cosmic web filament, stretching across 500 million light-years, connecting galaxy clusters in a network of dark matter and ordinary matter that forms the backbone of cosmic structure. The filament is not empty space, but a river of matter flowing through the universe. Dark matter particles, invisible to our eyes but detectable through their gravitational effects, form the filament's core structure. Along this dark matter highway, ordinary matter, hydrogen and helium gas, flows like a cosmic river, feeding the galaxy clusters at the filament's intersections. As we travel along the filament, we observe the cosmic web in all its glory. The universe is not uniformly filled with galaxies, but rather organized into a vast network of filaments, sheets, and voids that resembles a three-dimensional spiderweb. The filaments connect dense nodes where galaxy clusters form, while the voids between them are vast regions of near-empty space that can span hundreds of millions of light-years. The filament we are following is particularly active. Gas flowing along its length is being heated by shock waves created by the gravitational collapse of the structure itself. These shock waves accelerate particles to high energies, creating a faint glow of radio emission that can be detected by the most sensitive telescopes. The filament is essentially a cosmic particle accelerator, stretching across hundreds of millions of light years. At regular intervals along the filament, we encounter galaxy groups and clusters forming at the intersections of multiple filaments. These cosmic cities are where the majority of galaxies in the universe reside, fed by the steady flow of matter along the filament highways. The largest clusters form at the intersections of the most massive filaments, creating superclusters that contain thousands of galaxies bound together by gravity. The filament also serves as a conveyor belt for galaxy evolution. Small galaxies formed in the quieter regions of the filament are gradually drawn toward the denser cluster environments, where they experience ram pressure stripping, tidal interactions, and eventually merge with larger galaxies. This cosmic urbanization process transforms spiral galaxies into elliptical galaxies and determines the final properties of the galaxy population. The structure of the cosmic web itself tells the story of the universe's evolution. The filaments formed from tiny density fluctuations in the early universe, regions where matter was slightly denser than average over billions of years. Gravity amplified these fluctuations, drawing matter into ever denser concentrations along the filament network. The pattern we see today is a fossil record of conditions in the universe when it was less than 1 million years old. The filament is also a highway for cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. These particles follow the magnetic field lines that thread through the filament, creating a cosmic superhighway that connects distant regions of the universe. Some of these cosmic rays will eventually reach Earth, carrying information about the most violent events in the universe. This is architecture on the largest scales possible, where the universe organizes itself into structures that span significant fractions of the observable cosmos. We approach the event horizon of a supermassive black hole, the point of no return where the escape velocity equals the speed of light and the normal laws of physics begin to break down. This cosmic monster contains the mass of 4 billion suns, compressed into a region smaller than our solar system, creating a gravitational field so intense that it warps space-time into impossible geometries. The approach to the event horizon is a journey through increasingly extreme physics. Time dilation becomes severe as we descend deeper into the gravitational well. Minutes for us correspond to hours in the outside universe. Light from distant stars appears blue shifted ahead of us and red shifted behind us, creating a tunnel of distorted starlight that shrinks as we approach the point of no return. The black hole's accretion disk spreads around us like a cosmic hurricane, with matter spiraling inward at thousands of kilometers per second. The disk glows with the heat of friction as gas particles collide and compress, reaching temperatures of millions of degrees. The inner regions of the disk shine with X-ray radiation, while the outer regions glow with optical and infrared light. Jets of plasma shoot out from the black hole's poles at 99% the speed of light, creating cosmic lighthouses that extend for thousands of light years. These jets are powered by the black hole's rotation, which drags space-time around with it and creates a region called the ergosphere, where it is impossible to remain stationary relative to distant stars. As we cross the event horizon, we experience something that has never been directly observed: the interior of a black hole. Contrary to popular belief, crossing the event horizon is not immediately fatal. The horizon appears as a one-way membrane through which we can pass, but from which no signal can ever return to the outside universe. To an outside observer, we would appear to freeze at the event horizon, our image redshifted into invisibility. Inside the black hole, Space-time is so severely curved that the normal concepts of space and time lose their meaning. The singularity at the center appears to be both everywhere and nowhere, a point of infinite density where the laws of physics as we know them cease to apply. Some theories suggest that the singularity might be replaced by exotic structures, cosmic strings, naked singularities, or even gateways to other universes. The interior of the black hole is filled with the ghosts of everything that has ever fallen in stars, planets, gas clouds, and even light itself, all compressed and distorted by the extreme curvature of space-time. This information is not destroyed, but transformed in ways that challenge our understanding of quantum mechanics and general relativity. The black hole's interior might also be larger than it appears from the outside. The extreme curvature of space-time could create additional dimensions or pocket universes that exist within the black hole, but are invisible to outside observers. These regions might harbor exotic forms of matter and energy that exist nowhere else in the universe. This is the ultimate frontier of physics, where the most extreme conditions in the universe create phenomena that exist at the very edge of theoretical possibility. We emerge from the black hole's interior through a phenomenon that should not be possible according to classical physics, a white hole, connected to the black hole through a cosmic wormhole that serves as a bridge between distant regions of space-time. This Einstein-Rosen bridge allows matter and energy to flow from one location in the universe to another, creating a cosmic shortcut through the fabric of space and time. The wormhole appears as a tunnel of twisted space-time, its walls lined with exotic matter that has negative energy density. This exotic matter is what keeps the wormhole open, preventing it from collapsing under its own gravity. The matter creates a repulsive gravitational effect that pushes outward on the wormhole's walls, maintaining the tunnel's stability against the natural tendency of space-time to heal such extreme distortions. As we travel through the wormhole, we experience the ultimate in cosmic transportation. The journey that would normally take millions of years traveling through normal space is completed in minutes. As we slide through the curved space-time of the wormhole's interior, the walls of the tunnel glow with Hawking radiation, the quantum mechanical emission that results from the interaction between matter and the extremely curved space-time. The wormhole's interior is a place where causality itself becomes questionable. Information can flow backward through time, creating closed time-like curves that allow effects to precede their causes. This violation of causality is what makes wormholes so controversial in theoretical physics. They seem to allow for time travel and the creation of paradoxes that challenge our understanding of the universe's logical structure. The exotic matter that keeps the wormhole open is unlike anything that exists in the normal universe. It has negative energy density, which means it weighs less than nothing and creates a repulsive gravitational effect. This matter might be composed of virtual particles borrowed from the quantum vacuum, or it might be a form of matter that exists only in the extreme conditions found near black holes and other exotic objects. The wormhole connects two regions of space-time that are normally separated by vast distances. The black hole we entered might be in one galaxy, while the white hole we are approaching could be in a completely different galaxy, billions of light years away. This cosmic shortcut allows for instantaneous communication and travel between distant regions of the universe. The white hole that marks the wormhole's exit is the time-reversed version of the black hole we entered. While black holes swallow everything that comes near them, white holes expel matter and energy at tremendous rates. The white hole appears as a brilliant source of light and particles, surrounded by expanding shells of matter that have been ejected from its interior. The wormhole's existence has profound implications for the nature of space and time. If such structures exist, then the universe might be far more connected than we imagine. with networks of wormholes linking distant regions and allowing for the rapid transport of matter, energy, and information across cosmic distances. This is speculative physics at its most extreme, where the boundaries between science and science fiction become blurred in the face of phenomena that challenge our deepest assumptions about reality. We approach a cosmic phenomenon that exists at the intersection of the very large and the very small. A region where quantum mechanics and general relativity collide in spectacular fashion. Here, the quantum foam of space-time becomes visible, creating a seething froth of virtual particles and microscopic black holes that pop into existence and disappear faster than light can travel between them. At the smallest scales, space and time lose their smooth, continuous nature and become discrete and granular. The Planck scale, where distances are measured in units of 10 to the negative 35th meters and time intervals in units of 10 to the negative 43rd seconds, represents the fundamental limit of space-time itself. Below this scale, the very concepts of space and time break down, replaced by something far stranger and more fundamental. The quantum foam is filled with virtual particles that exist for impossibly brief moments before annihilating each other and returning their borrowed energy to the vacuum. These particles are not directly observable, but their effects are real and measurable. They create a background of energy that permeates all of space, contributing to the cosmological constant that drives the accelerating expansion of the universe. Microscopic black holes, smaller than atoms but containing the mass of mountains, appear and disappear in the quantum foam. These primordial black holes are remnants of the extreme conditions that existed in the first moments after the Big Bang, when the universe was so dense that random fluctuations could create black holes from pure energy. Most of these micro-black holes evaporate instantly through Hawking radiation, but some might survive as relics of the early universe. The quantum foam also contains cosmic strings, one-dimensional defects in space-time that are thinner than protons, but potentially billions of light-years long. These strings carry enormous amounts of energy and create gravitational fields that can bend light and distort space around them. If cosmic strings exist, they would be among the most exotic objects in the universe, vibrating like cosmic guitar strings and creating gravitational waves that could be detected by future instruments. The foam is also the birthplace of the fundamental forces of nature. At the Planck scale, the electromagnetic, weak, and strong nuclear forces merge into a single, unified force, creating conditions that existed nowhere else in the universe since the first moments after the Big Bang. The quantum foam is a laboratory for grand unified theories, where the deepest symmetries of nature are revealed. In this region, the boundary between matter and space-time itself becomes meaningless. Particles and the vacuum are interchangeable, with virtual particles constantly being created from nothing and disappearing back into the void. This process is what gives the vacuum its energy and creates the mysterious dark energy that dominates the universe. The quantum foam also contains the information that defines the laws of physics themselves. The fundamental constants of nature, the speed of light, the strength of gravity, the mass of the electron might be encoded in the structure of the foam at the Planck scale. This suggests that the laws of physics are not arbitrary, but are determined by the quantum mechanical properties of space-time itself. This is reality at its most fundamental level, where the distinction between matter and space disappears and the universe reveals its deepest secrets. We witness the birth of a new universe within our own, a cosmic bubble that expands through a process called eternal inflation, creating an entirely separate space-time with its own physical laws and constants. This baby universe appears as a rapidly expanding sphere of space that grows faster than the speed of light, driven by the explosive energy of a false vacuum decay event. The process began with a tiny fluctuation in the quantum foam, a region where the fundamental energy field that drives inflation became unstable. This instability triggered a phase transition, like water suddenly turning to ice, but on a cosmic scale. The energy released by this phase transition created a new region of space-time that began expanding exponentially, doubling in size every fraction of a second. The baby universe is not just a larger version of the space around it. It is a completely separate cosmos with its own unique properties. The fundamental constants of physics might be different there, with different values for the speed of light, the strength of gravity, or the mass of elementary particles. The number of spatial dimensions might even be different, creating a universe where the familiar 3 dimensions of space are replaced by something completely alien. As the baby universe expands, it becomes causally disconnected from our own cosmos. Information cannot flow between the 2 universes, making the baby universe essentially unreachable from our perspective. To an observer inside the baby universe, it would appear to be the entire cosmos, with no awareness of the parent universe from which it emerged. The boundary between the 2 universes is a fascinating region where the laws of physics undergo dramatic changes. Space and time themselves might have different properties on either side of the boundary, creating a cosmic membrane that separates 2 entirely different realities. The boundary acts like a one-way valve, allowing the baby universe to expand outward while preventing any communication with the parent universe. The inflation process that drives the baby universe's expansion is powered by dark energy, but not the same dark energy that accelerates the expansion of our own universe. This is a more exotic form of energy associated with the false vacuum, a state where the quantum fields that define the fundamental forces of nature are trapped in a high-energy configuration that wants to decay to a lower-energy state. The baby universe will eventually undergo its own Big Bang. As the inflation process ends and the energy driving the expansion is converted into matter and radiation, this will create a hot, dense fireball, similar to the one that marked the beginning of our own universe, followed by billions of years of cosmic evolution that might produce stars, galaxies, and even life. The existence of baby universes suggests that our cosmos might be just one member of an infinite multiverse, a vast collection of universes with different physical laws and properties. Some of these universes might be similar to our own, while others might be so alien that they would be completely unrecognizable to us. This is cosmology at its most speculative, where the birth of universes becomes a natural consequence of the quantum mechanical properties of space-time itself. We approach the most distant observable objects in the universe, galaxies so far away that their light has traveled for over 13 billion years to reach us, showing us what the cosmos looked like when it was less than 1 billion years old. These ancient galaxies are time machines, preserving the conditions that existed in the early universe. When the first stars were forming and the cosmic dark ages were finally coming to an end, the galaxies appear as faint, red-shifted smudges of light, their wavelengths stretched by the expansion of the universe itself. What would normally be blue and ultraviolet light from hot, young stars has been shifted into the infrared part of the spectrum, requiring specialized instruments to detect and study these cosmic fossils. The redshift is so extreme that these galaxies are receding from us at speeds approaching the speed of light. These early galaxies are smaller and more chaotic than the grand spiral and elliptical galaxies we see in the modern universe. They are actively forming stars at rates that dwarf anything we observe today, creating new suns at rates hundreds of times faster than the Milky Way. The star formation is so intense that these galaxies shine with the light of billions of massive, short-lived stars that will explode as supernovae within just a few million years. The galaxies are also rich in primordial elements, containing almost no heavy elements beyond hydrogen and helium. This is because they formed before generations of stars had time to create and distribute the carbon, oxygen, silicon, and iron that make up the rocky planets and complex chemistry of the modern universe. The first stars in these galaxies were pure hydrogen and helium, burning with nuclear fires that had never before existed in the cosmos. The supermassive black holes at the centers of these early galaxies are growing rapidly, fed by the abundant gas and ongoing galaxy mergers that characterized this early epoch. These black holes are already millions of times more massive than our Sun, despite forming in an era when the universe was less than 1 billion years old. Their rapid growth challenges our understanding of how such massive objects could form so quickly in the early universe. The space between these early galaxies is filled with a warm, ionized gas that glows with the light of the first stars. This is the epoch of ionization, when the first generation of stars began to shine and their ultraviolet radiation ionized the neutral hydrogen that filled the universe. The process transformed the cosmos from a dark, neutral state to the ionized, transparent universe we see today. The galaxies are connected by streams of dark matter and gas that will eventually merge to form the large-scale structure of the modern universe. We can see the cosmic web in its infancy, with filaments of matter connecting the early galaxies and feeding their rapid growth. This is the universe under construction, building the foundations for the cosmic architecture that will persist for billions of years. As we observe these ancient galaxies, we are looking back in time toward the very edge of the observable universe, approaching the cosmic microwave background radiation that marks the moment when the universe became transparent for the first time. We reach the edge of the observable universe, the cosmic microwave background radiation that marks the moment when the universe became transparent for the first time. This wall of ancient light surrounds us in all directions, a spherical shell of radiation that has been traveling through space for over 13 billion years, carrying information about the conditions that existed when the cosmos was only 380,000 years old. The cosmic microwave background appears as a uniform glow of radiation with a temperature of just 2.7 degrees above absolute zero. This radiation is the cooled remnant of the hot, dense fireball that filled the universe in its earliest moments. When the universe was young, it was so hot and dense that electrons and protons existed as separate particles, creating a cosmic soup that was opaque to light. Photons could not travel far before being scattered by free electrons, making the universe a glowing fog. But as the universe expanded and cooled, it reached a critical temperature where electrons and protons could combine to form neutral hydrogen atoms. This event, called recombination, made the universe transparent for the first time. The photons that had been trapped in the cosmic fog were suddenly free to travel through space, carrying with them a snapshot of the universe's conditions at that moment. The cosmic microwave background is remarkably uniform, varying in temperature by only a few parts in 100,000 across the entire sky. But these tiny variations are incredibly important. They represent the seeds of all the structure we see in the modern universe. Regions that were slightly denser than average eventually grew into galaxy clusters, while regions that were slightly less dense became the cosmic voids that separate them. The patterns in the cosmic microwave background tell us about the fundamental properties of the universe itself. The size and shape of the temperature variations reveal the geometry of space-time. The the amount of dark matter and dark energy, and the rate of expansion of the universe. This radiation is a cosmic fossil, preserving information about the universe's birth in exquisite detail. As we study the cosmic microwave background, we can see the signatures of cosmic inflation, the exponential expansion that occurred in the first fraction of a second after the Big Bang. The quantum fluctuations that were stretched to cosmic scales during inflation are visible as the temperature variations in the background radiation. These fluctuations are our best evidence for the inflationary epoch that shaped the early universe. The cosmic microwave background also contains information about the first moments after the Big Bang, when the fundamental forces of nature were unified and the universe existed in states that cannot be recreated in any laboratory. The polarization patterns in the radiation might reveal the signature of primordial gravitational waves, ripples in space-time itself that were created by the violent expansion of the early universe. This is the farthest we can see into the past, the ultimate horizon beyond which the universe becomes opaque to electromagnetic radiation. Beyond this wall of ancient light lies the true beginning of everything, the moment when space and time themselves came into existence and the cosmic story began. We begin our final approach to the Andromeda Galaxy, and the scale of what awaits us becomes overwhelming. This cosmic island contains over 1 trillion stars, 4 times more than our home galaxy. From our vantage point, Andromeda appears as a magnificent spiral structure, its arms sweeping through space in elegant curves that have been shaped by billions of years of galactic rotation. The galaxy's spiral arms are not solid structures, but density waves that move through the galactic disk like ripples on a cosmic pond. These waves compress the interstellar gas as they pass, triggering bursts of star formation that light up the arms with brilliant blue and white stars. The arms appear bright because they contain the youngest, hottest stars in the galaxy, massive giants that burn through their fuel quickly and die in spectacular supernova explosions. Andromeda's central bulge glows with the steady light of ancient red giant stars, some of which formed when the universe was less than half its current age. These stellar elders have watched the galaxy evolve for billions of years, surviving multiple passages through the spiral arms and witnessing the rise and fall of countless generations of stars. The bulge contains over 100 billion stars packed into a region just a few thousand light-years across, creating a stellar density that is thousands of times higher than in our local neighborhood. The galaxy's disk is warped and twisted, distorted by gravitational interactions with its satellite galaxies. This warping creates vertical waves that ripple through the disk like a cosmic flag flapping in the wind. The distortion is evidence of Andromeda's violent past, a history of collisions and mergers that have shaped its current structure. As we approach the galaxy's outer regions, we encounter the extended halo of dark matter that surrounds Andromeda like an invisible cocoon. This halo contains 10 times more mass than all the visible stars combined. Yet it can only be detected through its gravitational effects on the stars and gas within the galaxy. The dark matter halo extends for hundreds of thousands of light-years beyond the visible edge of the galaxy, creating a gravitational influence that reaches almost to our own Milky Way. The galaxy's rotation is unlike anything in our solar system. While planets orbit the sun in orderly, predictable paths, the stars in Andromeda move in complex orbits that are influenced by the galaxy's spiral structure, central black hole, and dark matter distribution. Some stars follow nearly circular paths around the galactic center, while others trace elongated ellipses that take them from the inner regions to the outer edges of the galaxy. Andromeda is also home to a complex ecosystem of satellite galaxies, small stellar systems that orbit the main galaxy like cosmic moons. These satellites are being slowly torn apart by Andromeda's gravity. Their stars stripped away to form stellar streams that trace their orbital paths. The largest satellites, including M32 and M110, are massive enough to survive this tidal disruption. But smaller satellites are completely destroyed. Their stars absorbed into Andromeda's halo. The galaxy is approaching us at 250,000 miles per hour, destined to collide with our own Milky Way in approximately 4 billion years. This cosmic collision will reshape both galaxies, creating something entirely new and magnificent. We plunge into Andromeda's spiral arms, where stellar nurseries are giving birth to new stars at a rate that dwarfs anything in our own galaxy. These star-forming regions are cosmic cities of creation, where giant molecular clouds collapse under their own gravity to form clusters of hot, young stars that will illuminate the galaxy for millions of years to come. The spiral arms are outlined by brilliant blue supergiant stars, each one dozens of times more massive than our Sun and burning with the intensity of 100,000 suns. These stellar monsters have lifespans measured in millions, rather than billions, of years, living fast and dying young in spectacular supernova explosions that seed the galaxy with heavy elements and trigger the formation of new generations of stars. Between the spiral arms, we encounter the galaxy's older stellar population, a mix of red giant stars and main sequence stars like our own Sun. These stars follow more sedate orbits around the galactic center, their motion governed by the galaxy's overall gravitational field, rather than the density waves that define the spiral structure. This is where the galaxy's long-term stellar evolution plays out, with stars slowly aging and evolving over billions of years. The interstellar medium in Andromeda is a complex web of gas and dust that serves as the raw material for future star formation. Hot, ionized gas from supernova explosions and stellar winds creates vast bubbles of million-degree plasma that extend for hundreds of light years. These superbubbles are connected by networks of cooler gas filaments that channel material between different regions of the galaxy. Dust lanes thread through the spiral arms like cosmic highways, marking the densest concentrations of interstellar matter. These dust lanes are where the galaxy's chemical evolution takes place, with heavy elements from dying stars mixing with primordial hydrogen and helium to create the complex chemistry necessary for planet formation and life. The dust grains themselves are cosmic factories, catalyzing chemical reactions that would be impossible in the vacuum of space. The galaxy's magnetic field permeates the entire disk, creating invisible highways that guide the flow of charged particles and cosmic rays. This magnetic field is generated by the motion of ionized quark in the galactic disk, creating a dynamo effect that amplifies and sustains the field over billions of years. The field lines follow the spiral structure of the galaxy, creating a complex pattern that influences everything from star formation to the propagation of cosmic rays. Andromeda's spiral arms are also home to some of the largest star-forming complexes in the local universe. These giant HII regions, ionized by the radiation from massive star clusters, glow with the characteristic red light of hydrogen emission. Some of these regions are so large that they would span significant fractions of our own galaxy's disk, containing enough material to form millions of stars like our Sun. The spiral arms are not permanent features, but transient patterns that rotate through the galaxy at a different speed than the stars themselves. This creates a cosmic traffic jam effect, where stars and gas are compressed as they enter the arms and then spread out as they exit. This compression triggers the star formation that makes the arms so bright and beautiful. We approach the heart of Andromeda, where a supermassive black hole containing the mass of 100 million suns dominates the galactic center. This cosmic monster is 25 times more massive than the black hole at the center of our own galaxy, creating a gravitational influence that shapes the motion of billions of stars across the central regions of Andromeda. The galactic center is a place of extreme stellar density, where stars are packed thousands of times more closely than in our solar neighborhood. Here, close encounters between stars are common, leading to exotic stellar interactions that are virtually impossible in the galaxy's outer regions. Binary star systems are torn apart by gravitational interactions, while single stars can be flung out of the galaxy entirely by close encounters with the central black hole. The black hole itself is surprisingly quiet compared to the active galactic nuclei we have encountered elsewhere in the universe. It is not actively feeding on large amounts of material, which means it is not producing the brilliant jets and intense radiation that characterize quasars and other active galaxies. Instead, Andromeda's central black hole exists in a state of relative dormancy, occasionally flaring up when a star or gas cloud ventures too close. The galactic center is surrounded by a nuclear star cluster, a dense concentration of stars that formed from gas that was funneled toward the galaxy's center by gravitational instabilities. This cluster contains millions of stars packed into a region just a few light years across, creating a stellar environment unlike anything else in the galaxy. The stars here are predominantly old and metal-rich, formed from gas that had been enriched by previous generations of stellar evolution. The central regions of Andromeda also contain a complex network of gas streams and dust lanes that spiral inward toward the black hole. These structures are the galaxy's circulatory system, channeling material from the outer regions toward the center, where it can fuel star formation or feed the central black hole. The gas flows are shaped by the galaxy's bar structure, an elongated concentration of stars that funnels material inward through gravitational torques. The black hole's gravitational influence extends far beyond its immediate vicinity, affecting the orbits of stars throughout the central bulge of the galaxy. The stellar orbits here are complex and chaotic, influenced by the black hole's gravity, the galaxy's bar structure, and the gravitational effects of the dense star clusters surrounding the black hole. Some stars follow highly eccentric orbits that take them from the outer regions of the bulge to within a few light years of the black hole itself. The galactic center is also home to some of the galaxy's most exotic stellar populations. Here we find populations of blue straggler stars, objects that appear younger than they should be based on their location in such an old stellar environment. These stars have been rejuvenated by stellar mergers or mass transfer from companion stars, giving them a second lease on life in the crowded environment of the galactic center. This is the engine room of the galaxy, where the central black hole's gravity orchestrates the complex dance of billions of stars and shapes the galaxy's overall structure and evolution. We discover something extraordinary in Andromeda's halo, a vast graveyard of disrupted satellite galaxies. Their stars scattered in long tidal streams that wrap around the galaxy like cosmic spiderwebs. These stellar streams are the fossil remains of smaller galaxies that were torn apart by Andromeda's gravity. Their stars redistributed throughout the galactic halo in intricate patterns that tell the story of the galaxy's violent past. The most spectacular of these streams is the giant stellar stream, a river of stars that extends for hundreds of thousands of light years and contains the remnants of what was once a substantial dwarf galaxy. The stream is so large that it wraps around Andromeda multiple times, creating a complex